Hi, welcome to the 18th lecture in this series. So in the last lecture, I was in the process of completing the proof that the tangent space is n-dimensional. And so I was almost done. Now let me resume from this point. So if we recall quickly what we have, the strategy of the, so here's the main statement. The theorem is that this is what we are aiming for, n manifold and TPM has dimension n. So the idea of the proof was as follows. We take a chart around the point P, u comma phi, and then the main idea is just this series of isomorphisms. So we had to prove that if you have an open subset of a manifold, then and a point inside that, then the tangent space to the open set at that point is the same as the tangent space to the manifold at that point. Assuming one had this, then one has this series of isomorphisms. TPM is isomorphic to TPU, and because this chart almost by definition of smoothness is a smooth map, is a diffeomorphism. It sets up the derivative of phi sets up an isomorphism between TPU and T phi of PU1, which is what I have here. And then again U1 is an open subset of Rn, therefore its tangent space, the tangent space to U1 at phi of P, same as this. Finally one had this. This was what I had started with a couple of lectures ago, and in fact this is the last isomorphism is the most the one with non-trivial content. The remaining these other three are easier in some sense, because the last isomorphism one had to use a little bit of analysis to get this. And well, so I was in the process. So in this chain of isomorphisms, all will be done if we show that for any open subset of a manifold, TPU is isomorphic to TPM. That's what we are aiming for. And we needed a small lemma for this. So the lemma is that if phi belong to C infinity M is identically 0 on some open set containing P, and if V is any tangent vector at P, tangent vector to M at P, then V of phi is 0. So in other words, even if the function phi is not globally 0 but 0 near a neighborhood of P, V of phi should be 0. And again the interpretation of this is that the derivative of a function, if a function vanishes in an open subset, then the derivative of the function at any point inside the open subset is 0. So in order to prove this, what I did was I took a chart around this point P. Then I looked at then we can assume that the chart is actually contained in U. Now here's the main idea. So if let f be a C infinity function on M with support contained in this. So now the picture is, so this is the point P. This is a big open set, and I can assume that U tilde is actually contained in U, and this function is supported, the support of the function is contained in U tilde, and moreover its value at P is 1. So to say that the support is contained in u tilde in particular implies that it's identically 0 outside u tilde. So if I look at this product function f times the original function phi, then it's actually just the 0 function, because if x is inside u tilde, then phi is 0. On the other hand, if x is outside u tilde, this f is 0. G is identically 0, and then, but if I take v of g and apply Leibniz rule, I get this. Then finally, I get v of phi 0. So let me quickly point out how we can get a C infinity function with support contained in u tilde and f of p is 1. Construction of f. Well, we had a chart u tilde and a point P, and now I've used phi in a different sense here. So for a chart, let me use a map alpha, and it goes to some u tilde 1 alpha of p. By changing alpha to the map alpha of x going to alpha of x minus alpha of p, we can assume that alpha of p is actually 0. Just by translating this map alpha in Rn, I can assume alpha of p is 0. And once we have alpha of p is 0, also we can assume u1 tilde contains the ball of radius, let's say 3, centered at the origin. This is a set of so we can assume, also we can assume this by multiplying alpha by a suitable large positive constant. In other words, you multiply, so consider C times alpha of x, where C is some large positive number. Then we can assume that the image contains the ball. So this is u1 tilde, and now we have 0 and we have the ball here. So this is 0, and we have a ball of radius 3 in the image. Well, we have seen already that we can construct a C infinity function now. We know that there is a C infinity function C infinity function g on Rn such that g of x is identically 1 for all x in the ball of radius 1 centered at the origin. G of x is identically 0 for all x in Rn minus the ball of radius 2 and everywhere and even though we don't need this last thing, I'll just write it down, and g of x lies between 0 and 1 for all x in Rn. So I really don't need the ball of radius 3. I just have to work with the ball of radius 1 and 2. So this is 1, radius 1, and this is radius 2. And my function g is identically 1 inside this smaller ball. Inside this orange ball, the function is 1, and outside everywhere it is 0. So g is 0 here and g is 1 inside. And in this and gap between these two balls, it varies between 0 and 1. So what we can do is use this g to get a similar function on the manifold, which is my f. Define f from M to R by, well, so we have to work with, so before I write this, so let's see, here I had the ball of radius 2 and ball of radius 1. This is in U1, U tilde 1, which is in Rn. Now using this alpha, which was the homeomorphism, diffeomorphism from U tilde to U tilde 1, I'll get corresponding sets in the manifold. Let equal to phi inverse of this first ball B10 and B equal to phi inverse the second ball B20. Then I define f from M to R by f of x equals. So the idea is simple. So I'm going to essentially use if my x belongs to this U tilde, then I'll just use this function g via the map alpha. So f of x equals g of alpha of x if x is in U tilde, and then is equal to 0 if x belongs to M minus U tilde. So this has been defined in a piecewise way, sort of. So essentially, note that for the moment, if we assume that f is smooth, note the following. Note that if x belongs to what I call this A, then f of x, oops, there was a small correction here, it is not phi, rather I call the chart map as alpha now. So alpha. So note that if x belongs to A, then alpha x by definition will belong to B10, therefore g of that will be 1. And if x belongs to M minus rather U tilde minus B, then f of x is, well, if x belongs to U tilde minus B, then when I go via this chart map, I'll end up with this in this green part in U1 tilde, and we know that g is 0 there. So f of x would be 0. So in short, now in fact this second thing, that f of x is identically 0 outside u tilde minus b, will also imply that this will also imply that f is smooth on u tilde, smooth on M. Whenever we define functions in a piecewise fashion like this, one has to be careful that smoothness holds everywhere. One has to check that. For instance, in this simple case, if x belongs to u tilde, anyway it's a composition of smooth functions, therefore it is smooth. And if x belongs to m minus u tilde as well, well, here this is the constant function which is smooth. Though ideally, actually, when one talks about smoothness, the domain should be an open set. So here one has to be changed slightly and regard it as a function on m minus u tilde closure. Then the constant function is smooth. Then the task becomes what happens. So here, to be very precise, I would want to define it as if x belongs to this, and if x belongs to m minus this u tilde. Right. No, this is fine. However, when checking smoothness, one will have to segregate into two cases. So one is x belongs to m minus u tilde closure, which is an open set. There f of x is identically 0. Similarly, if x belongs to u, which is an open set, f is smooth. The question becomes what happens if x belongs to the boundary of u tilde. But it's not an issue, because if x belongs to u tilde minus b, already f of x is 0. So therefore, the point is that this is our b. Rather, this is, it might be a distorted ball. So this is our b. And the point is that u tilde minus b in this entire portion, the function f of x is 0 anyway. And even outside this u tilde, we have defined it to be 0 by this here. So the point is, even if you are on the boundary of u tilde, it's not an issue. In an E, you can find a small neighborhood such that in that neighborhood, the function is identically 0. So it's a constant, therefore it's smooth there as well. So this proves that f is smooth everywhere, and it has the required property. Well, the thing is that since it's identically 1 on B, and the point P certainly belongs to this B, because point P corresponds, the way we set up things, P actually corresponds to the origin in Rn, which belongs to the ball of radius 2, certainly ball of radius 1. Therefore, f of x will be identically 1 at P. And the support of this function by definition is inside B, which is inside u tilde for sure. That's what we wanted. So this completes a proof that if a function vanishes in an open set, then now let's see how this is going to help us in the overall scheme of things. So we were trying to prove that. So we had this TPU, and then we wanted to claim that this map DIP, the derivative of the inclusion map, is an isomorphism. So let's so what does this map do? First, before we prove injectivity and surjectivity, let's just check see what this map does. So if I start with a V here, TPU, then DIP of V should give me an element of TPM. So in other words, it should act on a C infinity function on and C infinity function on M. Then by definition, DIP of V acting on phi is supposed to be V of, well, first I go via I and then phi of I. So this is my, in other words, this map phi composed with I is nothing but the restriction of phi. Phi is defined on all of M, but I'm just restricting it to this open set U, and then I act it, then I take the directional derivative along V. Well, let's see why this is injectivity. Suppose DIP of V1 equal to DIP of V2 for some tangent V1, V2 in TPU. Then actually, right. So rather than this, let me just, these are linear, this is a linear map. We already know that DIP is linear. So when we are in the realm of linear maps, to check injectivity, I just have to check that the kernel is 0. So suppose I have this, I would like to say that V is 0, i.e. DIPV of phi is 0 for all phi in C infinity M. So now this is by definition what I've written here. So this is equal to V of phi composed with I is equal to 0 for all this phi in C infinity M. So in other words, what we are saying is that if I take a C infinity function on, so here's U and it's sitting inside some big manifold M. I'm starting with a C infinity function on the big manifold, restricting it to U, and then I want to say then I have the property that V acting on such a function is 0. Well, if I can say that every C infinity function on this U arises as the restriction of some bigger C infinity function, then I would immediately conclude that V is identically 0. But it need not be true that every C infinity function on U is the restriction on some bigger function, on bigger C infinity function on M. So, but we really don't need that fact. So what we do need at this stage is that, so here at this stage, so V composed with this is 0 for every C infinity, this thing. So now let F belong to maybe not F, some other thing. C belong to C infinity U. So instead I'm going to use this fact, that previous statement about two functions agree, then the directional derivative should agree. So let me start with some function f in C infinity u. Now let u tilde be a chart containing P with, as before, you just put it in some chart u tilde. So what I'll do now is we can find C1 in C infinity u such that C of x equal to C1x for all x in u tilde. Oh, actually, let me use the same notation that I had used earlier. So recall that I had this A and B. So let me just expand this picture a bit. So I have this U, I have this U tilde, then I have two more sets. The innermost set was A, and containing A was B. Right. So what I want is we can find new function such that C of x equal to C1x for all x in B, no, rather all x in A, for all x in A, and C1 and C1x is 0 for all x in outside this B, essentially u minus B. And the way one would do it is we do whatever I did last time. Just let C1x equal to that function f of x that I had, the same f of x times C of x. Recall that f of x was identically 1 inside A. So when x is inside A, C1x will be equal to C of x. And maybe, okay, let me just, in this, maybe it's better to write this as C1x. Yeah, when x is inside A, C1x is C of x. And when x is outside B, well, when x is outside B, then this f of x is 0. So I'll get C1x equal to this. So this will be 0. And that's what I'm claiming here. Hence, as earlier, we can extend this new function C1 extend by 0. In other words, declare all values outside u to be 0 to all of m. So what we have now is we have a function C1 defined in all of m, which agrees with C on this small open set A containing P. So main thing is that C1 is defined on all of m, and C1 is identically equal to C on the open set A. we'll have to stop somewhat abruptly in this lecture. We'll stop here. Next time I'll take off from this point. Thank you.